Welcoming Colin Lennox, and he is the CEO of Eco Islands LLC. He builds self-organizing wetland bioreactors. These are passive wetland in a box systems, which are useful for reclaiming water from mines. And he also assists Arcology X to construct architectural ecologies that function as biodiverse habitats for homesteading on Earth and seasteading at sea. All right, Colin, I'll let you take it away.
Okay. Hey, everybody, thank you very much for coming out today. Hope you enjoy your lunch. And it isn't the rubber chicken special that they normally do at conferences. Yeah, so as mentioned, I'm Colin Lennox. Hi, CEO of Eco Islands. I have with me my co-author, Ms. Michaela McCord, just recently graduated with a master's in biotechnology, and we are publishing a paper for the Mine Influenced Waters something or other conference coming up here in West Virginia. And my primary line of work then is coal mining reclamation, specifically in acidified mine drainage, reclamation of iron, aluminum, and manganese. But also, before we got into that, it was nutrient remediation, point source and non-point source remediation. So water treatment once again. And just real quick, then everybody, is my shared screen? Everybody can see that? Thumbs up. I'm getting the nod. Okay, great. All right. Okay, thank you, Christina. So yeah, what you see in the background there is our 8 self-organizing wetland bioreactors. I did these for a mining client. I'm not sure if I'm supposed to say who they are or not, but everything's in compliance, so I guess it probably doesn't matter all that much. And this is a coal mining reclamation site in central Pennsylvania. It's about 45 minutes north of my home here in Altoona, PA, which is, if anybody knows Penn State or main campus in central Pennsylvania, I'm 45 minutes south of that, just to give you an idea. Smack dab in the middle of, Pennsylvania coal mining country, essentially. So we built these systems in a, oh, hey, Frank's on board too. Everybody, hi, this is Frank Italian. I don't know if you can see him. He's another one of my co-workers with Arcology X. But yeah, so what we do then is reclamation and bioremediation of acidified mine drainage. But before we get into all that, let's talk about wetlands. Let's see if I can get this thing to go forward. There we go. Okay, what is a wetland? Because that is one of the key questions that anybody who is developing BLIS, biological life support systems, ECLIS, environmental control life support systems, whatever acronym you want to use, for understanding how terrestrial ecologies are relevant in their understanding towards keeping us up there and alive long-term, permanently, sustainably. So what is a wetland, essentially? So basically, it holds water most of the time. Water moves through it, so it's a flow-through system. There's high surface area to volume, and that gets into the biofilm attachment, which we'll talk about a little bit more. High biomass to volume then as well. One second here. Too many moving things. I'm distracting myself over there. High biomass to volume is really key. Think about the differences between a biotic and an abiotic system. These are, of course, biotic and biotic, all happening right on top of one another with, 4 billion years of evolution backing it up. They cycle, the wetlands cycle matter and energy in lots of different ways, as mentioned, biotic and abiotic. And probably most importantly, and the thing that isn't really necessarily obvious, and certainly wasn't to me when I started doing this years ago, is that they self-organize. And that's really why we're calling them self-organizing wetland bioreactors. And they're based off of Gibbs free energy, or the prevailing atmosphere. To the biologists in the room, it's the amount of ATP per the metabolic triplets, so that there is a selective pressure towards metabolic pathways that produce more ATP per glucose. And then, so thinking Krebs cycle, citric acid cycle, fermentation, think about those different metabolic pathways. That's what appears to be the primary determining factor and what allows for self-selection and organization in a flow through open, and once again, open environment. Let's see, like a wetland is. Okay, so what is a bioreactor then? I mean, it may seem kind of obvious, but we want to talk about it a little bit. It does predictable and reproducible work. And I do mean work as in that classical sense of, energy in, energy out. There is some kind of an output. It is doing something for you, even if it is just a passive gravity flow through system. It is still achieving work. In this case, you are capturing and remediating mine drainage constituents like iron, aluminum, manganese, suspended solids, and the like within a system. Um, and it is essentially, I like to think of it as a biological engine. To the engineers in the room, it's essentially a wetland is in some ways, when it is allowed to self-organize, is a multi-fuel, multi-oxidant reaction system that is determined by it uses the most productive, energy dense metabolic pathways first, aerobic metabolism in this case. That's why we're these big bodies, we can breathe. It's supporting this huge ecology and body that is human beings. And biological engine ruled by the laws of conservation of mass and energy. Of course, you're never getting away from those. That catalyzes reactions producing useful byproducts. Now, I'd call this BISRU, but biological in situ resource utilization is, going back to other NASA terms, that's kind of, the way you want to think about it in your head. Now, a natural wetland, self-selecting and organizing, let's see, EPA, or Environmental Protection Agency, calls it natural attenuation. I like that term. That's why I threw it in there. You never hear it used by anybody, but it rings true to me. Whereas a constructed or a manufactured wetland are the conscious selection of environments to cycle matter and energy. It's a wetland in a box, say, the self-organizing wetland bioreactor, whose purpose is specifically to sequester and separate the different components going through that system based off of their redox and the metabolic pathways. Bioreactors, specific and by definition, the way I look at it, the way that seems useful, are natural wetlands, methane digesters, reclamation ponds, fish tanks, greenhouses, wastewater treatment plants, wine and beer vats, although technically they would not be flow-through systems. They're batch reactors, but that still kind of counts. It's still a bioreactor. But then in the larger definition, people, plants, box turtles, or my dog River. And that one picture there with River, she does not see that box turtle, by the way. It blew my mind. On the top picture there, that's one of my interns. That's Nick. He's 6'7", so that tells you the size of that reactor right there. He's a tall fella. Okay, going to the redox ladder then. This may be, some of you may be familiar with this. I guess mostly we're talking plant people here, so botanists. So if you're thinking, the requirements of both the production of oxygen as a byproduct of carbon dioxide being used as part of the metabolic pathway within photosynthesis, versus the, during its day cycle, then versus its night cycle, where it's still requiring oxygen nonetheless to maintain the aerobic system that is that plant. And the important thing here, well, a couple important things here, and I'm not going to dwell too terribly much on this one and get too into the weeds, because that's why you can have my email address after this, is that each one of those steps there that you're seeing between the aerobic down to the methanogenic is going back to ATP, and things like Krebs cycle and citric acid cycle is the amount of ATP produced per whatever the mass is of the glucose or the like that is being reduced through the system. And that electron transport then occurs through metabolism. The more ATP, the greater the selective advantage towards that predominant niche. And I'm using the term niche as in, like, that within that one specific little ecology, because they change. And that's that self-organization. As all the oxygen gets used up in the water, because you keep in mind that there is very low solubility of dissolved O2, diatomic oxygen, in water. And you think about the Caribbean right now, the Caribbean, I guess depending on how much money you grew up with, would the extreme heats that we are seeing are creating hypoxic environments versus some of the most productive environments on the entire planet. What's that fishing show? Deadly Catch. You know, you've got highly productive environments, even though it's all kinds of cold because of oxygen saturation, high levels of oxygen. So it's, you know, just because something's cold doesn't mean that it's slow in its metabolism. And then kicking over to then after you burn up all your oxygen, because, you know, it's anywhere from 7 to 12 milligrams per liter total, um, before reaching saturation in a water environment. After you burn all that up, and there's nothing more available, it kicks over to nitrate and nitrite reduction, so that it's the nitrogen pathways then, or the, excuse me, the available oxygen that was bound to the nitrogen that is the next greatest, what's called terminal electron acceptor. And this goes back to the metabolic pathways. Won't get too deep into it, but the idea then is that if you're starting 32 ATP for oxygen, I forget what it is for nitrogen. It's like 26 or somewhere and around there. But the idea is that for each one of those steps, then after all the nitrogen is used up, then you're going to kick off to your iron. And then you're going to kick to manganese and then selenium, which is a problem in, say, West Virginia, not necessarily where I live, but that stuff is really toxic. Selenate, selenite, selenide, elemental selenium, or the redox steps there. Then after that is sulfate, which it has a whole lot of potentials for pH adjustments by manipulating oxidative versus reductive environments within a wetland treatment train. And that's what the paper that Michaela and I are publishing speaks about. So if you want some more information, that's, you know, that'll be out here. Well, if anybody wants, we can just give you the PDF for it as soon as, just email myself, or please ask Dr. Johnson. She'll have it available as well. And after sulfate, then of course are the CO2 reduction or your methanogenesis. So that you get the idea there. If you're familiar with the term of a Winogradsky column, Sergei Winogradsky was a brilliant Ukrainian scientist and microbiologist. He was the one who discovered the nitrogen pathways. Like, that's how important this individual was. I was born in Kiev, 1850s or something. I mean, we're going back a far distance, but he developed what's called nowadays the classroom, very common in a microbiology classroom, Winogradsky column, which is doing the exact same thing as what our reactors are doing, except that column is straight up and down. It's vertical versus our systems, which are horizontal. Which means you have to have more seals to remove the oxygen. But once you get all the O2 out in the beginning and you're not reintroducing oxygen like most reclamation ponds would, you're not constantly fighting, you know, that Sisyphus stone where you're pushing it uphill and then it gets out of your hands. No, you know, just rolls all the way to the top, so to speak. And ways to measure then Winogradsky columns are by the electroconductivity, where you can literally measure it, and it's millivolts, sure, but it is still voltage. And the difference between aerobic versus methanogenic is about 0.9 volts. Blows my mind that you can do this with something that you can buy from Lowe's and sample, but it's really that simple, which is fortunate because the science is pretty accessible. Just nobody really knows it's a thing. Oh yeah, and then for the engineers, when we won that award from Ukraine, the Yuzhnoy from NASA and the Moon Village Association, which they were not biologists; they're mostly engineers. I figured that out pretty early on. They're used to more building like satellites and ICBMs. But for their context, then, is in this context and application, Sowbs are multi-fuel, multi-oxidant biological engines that self-organize to use each reductant and oxidizer sequentially based on the energy released and the availability of the metabolic pathways. That availability of the metabolic pathways is key. It's in an open environment. Otherwise, it would be back to a batch reactor. We're making wine. I mean, you wouldn't get all these effects in a batch reactor that have a single predominant metabolic pathway engendering that niche. You know, that's why it's got to be open to the entire environment, or else you might not have the opportunity to make that next step, and it would just halt at that one point. Say you're all out of O2, and you burn through all your nitrifiers, but then you don't have anything else to act as your terminal electron acceptors or donors, and it would just stop at that point, and then the system would essentially have the same characteristics of an abiotic system, say that doesn't have enough of a pH adjustment to engender whatever that next precipitation of whatever metals might be in the water, if it's an oxidizing environment. I know that that's about as clear as mud. My apologies, but once again, you can please get a hold of me after this. Now, I do believe metabolites can be skipped over if the genetics aren't present for one metabolic pathway. So I think they still can skip over it. It doesn't necessarily say that you're going to stop the entire process. It'll just skip over one of the potentials and then lose that opportunity to use other oxygen or electron acceptors. Once again, clear as mud, right?